Okay, so the Newman projection is a great way to measure the strain that exists in any given molecule. Remember, atoms do not like to get close to each other. They want to keep their distance from one another. The angle between atoms on adjacent carbons is called a dihedral angle or torsional angle. It is a 60-degree angle in this molecule shown between those two hydrogen on the front carbon and on the back carbon. Staggered conformations of molecules in which the bonds on the front carbon and the bonds on the back carbon are not lined up or overlapping are more stable, lower in energy, than their eclipsed conformations. This is where the bonds on the front carbon and the 3 bonds on the back carbon are parallel to each other or what we call eclipsing each other, okay? The difference in energy between these conformations is due to something called torsional strain. Here, the difference in energy is about 12 kilojoules per mole between the staggered conformation and the eclipsed conformation. Okay, so let's look at the rotation around a carbon-carbon bond of the molecule ethane. Okay, again, we know that we can get free rotation around a single bond, and we can see that when the carbons bonds to hydrogen, meaning the 3 bonds to hydrogen on the front carbon and the 3 bonds to hydrogen on the second carbon are staggered to each other, the molecule is lower in energy and much more stable than when those bonds are eclipsed or overlapping each other. It's possible the eclipsed conformation is 12 kilojoules per mole less stable because of electron pair repulsion between the eclipsing bonds. Okay, now again, we have 3 sets of carbon-hydrogen bonds that are eclipsing, so that would be 4 kilojoules per mole for each eclipsing interaction. With a difference of about 12 kilojoules per mole in stability at room temperature, this means that approximately 99+% of the molecules will be in the more preferred staggered conformation. Not surprising. Okay, now let's look at propane. Here, one of the hydrogens on the front carbon has been replaced by a methyl group. Now, when our bonds in the front carbon and back carbon are eclipsed, the energy strain is 14 kilojoules per mole, 2 kilojoules per mole higher than we saw with ethane. So let's do a little math. If each hydrogen-hydrogen eclipsing interaction that we saw with costs us 4 kilojoules per mole of stability, that total can be subtracted from the 14 kilojoules per mole to calculate the contribution of the methyl hydrogen eclipsing interaction. Okay, again with propane, when it is eclipsed, we have 2 carbon-hydrogen bonds that are eclipsing each other, 2 sets of carbon-hydrogen bonds that are eclipsing each other on the front carbon and the back carbon. Then we have this additional interaction where a carbon-carbon bond eclipses a carbon-hydrogen bond. By using what we learned from ethane, we can figure out that the carbon-carbon and carbon-hydrogen eclipsing bond, the bond in red down here, is worth 6 kilojoules per mole of energy. Finally, let's look at the conformational analysis for butane. Here, we have a methyl group on the front carbon and on the back carbon. Because of this, we have multiple staggered conformations that are slightly different and multiple eclipse conformations. Okay. The stability of the different staggered conformations actually differ a little bit now by about 3.8 kilojoules per mole. When the methyl groups are gouged to one another, as in these two pictures, okay, there is a steric strain and a higher energy conformation because those methyl groups, while not eclipsing, are near each other and they're both bigger groups, okay? This is opposed to the more stable anti-conformation. In the anti-conformation, they are 180 degrees apart from each other and they are not in each other's way. It is much more stable. The highest energy conformation for butane, unsurprisingly, results when the methyl groups eclipse one another. Each methyl-methyl eclipsing interaction actually accounts for 11 kilojoules per mole of energy. This is both torsional, meaning electrons interacting, and steric strain, because you have two big groups that are right on top of each other. Okay, we can actually use this conformational analysis of butane to get an energy cost for the different types of interactions that occur in molecules.